All right, I get started. Everyone, I'd like to start by acknowledging that NCM is situated on the lands of the Wurundjeri people. We pay respects to them, especially their elders and storytellers, as well as all First Peoples nationwide. NCM acknowledges that communication technologies have a long history here, far longer than European occupation. My name's Callum Stewart, and I'm the Partnerships and Industry Coordinator here at NCM. I'm also the producer on Quantum Futures, our newest industry-led exhibition. When I started developing this show, I kept coming across the same joke from physicists that no one actually understands quantum physics. Beyond the wry self-awareness of the joke, I thought it was an interesting place to start from. If even the experts in the field don't get it, what hope do we mere mortals have? It's from this perspective that NCM is building its industry space. Through collaboration with industry leaders, we're building a space that brings audiences in direct contact with the amazing technological advancements happening right in their backyard. Quantum is an incredibly complex and unpredictable field, but through this exhibition, NCM is introducing a new generation of scientists and engineers to the tiny but massive world of quantum. I want to say a huge thank you to the exhibition's partners, Equus, the ARC Centre of Excellence for Engineered Quantum Systems, and Q-CTRL. Their contributions were instrumental to the exhibition coming together, and we couldn't have done it without them. To launch the show, I'd like to introduce the speakers on our panel tonight. Moderating is Dr. Ben McAllister. Ben is an ARC DCRA Fellow at Swinburne University of Technology and an Equus Associate Investigator working at the interface of fundamental physics and quantum technology. Speaking tonight, we have Mick Conroy, Staff Product Manager at Q-CTRL and one of the creators of the Black Opal learning platform that features in the exhibition. Next to him is Dr. Kerstin, theoretical physicist researching quantum machine learning and the advantages of quantum models over classical ones. Finally, we have Dr. Michael Barson, an experimental physicist working in applied physics and quantum sensing. Thank you all for joining us tonight, and I'll pass over to Ben to get us started.
Great. Okay, yeah. Thanks, everybody. Thanks for coming. Thanks for coming, you guys, as well. I'm going to go slightly off book, though, for the first thing I want to talk about, just based on something that Callum just mentioned, and go down the panel and say, do you think you understand quantum physics? We'll start with you, Michael.
As much as I need to.
Okay, that's a good answer. It's a very practical answer. Kerstin?
Yeah, I would say I understand the tools I need in my job, but truly understanding is the hard word.
Yeah, for sure. And Kerstin does theory. And Mick?
I think I've got really good at a cocktail party level of understanding of quantum computing.
That's really important. And not easy.
Well, so you know who to talk to after the exhibition.
Yes, yeah, my natural environment.
That's going to be Mick there. Okay, great. So the first question that I'd love to hear from all of you on tonight is what do you think about the current state of quantum research, quantum technology, quantum in general in Australia? Anyone feel free to jump in with some thoughts?
So when I moved here 3 years ago, so I'm from Germany, maybe you hear my accent, I was really impressed how the different universities in Australia are connected, especially the quantum groups. So for me, quantum in Australia is a lot about the community and the collaboration between different research groups, but also universities and industry. So that was pretty special for me, coming from Europe, where it was much more divided into these typical university things. Yeah.
Yeah, I could probably tell off that. I think I'm really excited about sort of the current industry, the hunger that I'm seeing from people to learn about quantum computing in Australia. So my focus is more on quantum education side of things, and so I spend a lot of time in enterprise learning environments as well as sort of school-based learning environments. And there's just so much hunger for wanting to learn about it, and especially within schools. For example, you might see the interactive exhibition outside the current high score for the interactive exhibition is held by a Year 9 student. So see if you can beat their high score of 24, I think. So, yeah, I think that hunger that we're seeing across Australia is, something that really struck me.
And me as a researcher, I've had really good funding opportunities recently through sort of the current sort of state of interest in quantum, and you can pitch solutions that use quantum sensing, quantum physics. There's great appetite at the moment. People are interested in that.
Yeah, cool. I mean, there is this kind of thing that it's almost like a cliche in the Australian quantum space. For anyone who works in it, you've probably heard that we punch above our weight in quantum technology. That's a thing that people often say. A relatively small country, we seem to do a lot of stuff. Does anyone have any thoughts on that expression? And do you like it? Do you not like it? I don't know.
I think, like what Kerstin was saying before, the centres of excellence in Australia have been really good. Like they've punched out, they've done really well. You've had Equus and Centre for Quantum Computing, amongst others, and they've done some like world-class research. And there's been sort of a high concentration of these types of centre of excellence in Australia so far. And that's led to part of this sort of success as Australia in this space.
Yeah, it definitely seems like we do comparatively well in this space compared to like other areas with a reasonably small investment. So that's exciting. Okay, moving along. I'm interested to hear from each of you what you see as the most exciting, either like current applications or I'm going to say like near term, like you could be looking at using it in the next kind of year or two, quantum technologies. What do you think?
So in quantum sensing, I would say that we have already been using quantum technology for a long time. So I think quantum computing, you could speculate from how far away practical quantum computing is away, but quantum sensing is arguably being done since the 70s, ever since magnetic resonance. So NMR and MRI and things like that are, using quantum physics to perform measurement. And quantum sensing is good because it's the reason that quantum computers are hard to make is the reason that quantum sensors work well, because the environment fucks up our qubit and we just read that out. Where if you've got a computer, that's like bad, but for sensors, it's good.
Yeah. Turn a weakness into a strength. Why not?
I can piggyback on that, and I agree. Sensing is a really near-term opportunity and an area where Q-CTRL is doing a lot of work, especially in the quantum navigation space, where we're doing things like using quantum navigation. For those that don't know, is being able to do navigation in especially a GPS denied sort of situation. We don't have access to that sort of signal, and being able to use sort of the magnetic map of the Earth's, the surface of the Earth has different sort of magnetic signatures that you can use to orient yourself in where you are. And we just last month actually we sort of we have a new product called Ironstone Opal, and that's able to perform 50 times more effectively than the nearest sort of GPS alternative. And so that's effectively like quantum advantage in quantum navigation, which, as everybody knows, is quite a loaded term in quantum. So like that's something that we're seeing a lot of commercial application right now. So there's some really interesting work happening in that area.
Cool. Navigation space. Fascinating. Kerstin, any thoughts?
So I work in quantum computing, so I want to like quantum algorithms, not so much into sensing. And for me, one of the most interesting things are the hybrid formats where you combine classical computers with quantum computers, because our quantum devices are so small today that we can't, like, it's good to combine things and make things bigger. So for example, you have a big routine and you just select one routine, like one subroutine of it, and exchange it with a quantum one. So I work in quantum machine, and I'm really interested in like knowing what kind of problems we can solve with quantum machine learning, or where is it useful at all to find or to use quantum instead of full classical. And I think these hybrid formats are in the moment the most interesting ones.
Right. So something at the interface of classical and quantum computing. Because I guess maybe valuable for anyone here without as much of a background, when we talk about like quantum technology, people typically talk about like three kind of buckets of things. We talk about quantum sensing, which is like what Michael was talking about, using quantum systems that are inherently very, what would you say, unstable or sensitive to detect things. Quantum communication, which this museum is probably very heavily interested in, given the nature of it, and quantum computing, which you've just touched on. And I guess like historically people say like, oh, quantum sensing stuff is stuff that is now, and the other stuff is like stuff that is coming. But it's interesting to hear these examples that like maybe some of the applications of quantum computing can start a little earlier than when we have full scale quantum computers. So that's really cool. Maybe looking ahead a little bit, what do we think about the next 5, maybe 10 years? Where do you see any of those fields of quantum technology going?
So I think for me, like for the quantum computing, we will just have bigger devices which have less errors, so we can run algorithms better. But also like observing what happened in the last like years, I think we will have more crossover of different fields. Like I see, for example, at the universities that engineering students are also interested in quantum computing, not only the physicists, or like lawyers are thinking about what do we have to change to like go with this kind of quantum thing. And like I think that will be really interesting in the next 5 years.
And actually, to pick up on your point about these hybrid quantum classical applications, I think that's an area where we're seeing a lot of advancement even now, but will continue to grow over the next 3 to 5 years. These sort of QAOA optimization problems, and they specifically apply to problems like logistics or supply chain optimization, areas like that. And actually, we're already able to solve, find good solutions with today's cloud-based, quantum computers for problems that matter to organisations like Transport for New South Wales, or the Australian Army, for example, where they're looking at doing things like routing a convoy from one point to another or optimising traffic flows. And we're already able to solve problems for them at a slightly reduced scale. But even at that reduced scale, those problems are commercially worth solving. And then when you look ahead over the next 2 to 3 years, if we take those sorts of optimization problems that we're talking about, and then we look at the roadmaps for companies like IBM and Rigetti, IonQ that have building these quantum computers and how many qubits they anticipate having, we can see these sorts of solutions scaling to be able to fully solve these sorts of problems, these optimization problems in like 2028, those sorts of areas is sort of the prediction. So there's a lot happening in that space. And one last point on the 3 to 5 years is that I'm a product manager. I'm not a quantum physicist or a doctor like everybody else on the panel. So I actually see a lot of advances in usability of quantum computers over the next 3 to 5 years. So that optimization problem that I talked about with products like FireOpal that we have at Q-CTRL, you can actually run that with one line of code, and you just provide like a network as an input to that and a goal. And so that's super usable. You don't have to be creating massive circuits or anything like that. You can basically just feed in your business problem. And so that sort of usability, I think, will bring the power of quantum computing to a lot more organizations, make it a lot more usable, and they're able to really actually realize that over the next couple of years.
Yeah, so in the sensing space, I guess there's a lot of technology that's pretty easily deployable already. So there are a bunch of companies already who are kind of slapping these things in boxes and selling them. And I think that's going to, within 5 years, a lot of these companies are going to mature a lot more. You'll see more sort of easy use and streamlined quantum sensors that you could just go buy. In the computing space, I don't know much about algorithms or theory, but I think there's interesting stuff we'll have to have in the materials to improve, like things like noise at the surface and things like that dephase qubits. I think there's a lot of interesting things going on in making ultra pure materials, isotopic purifying, things like that, which I think be quite important for realizable quantum computers.
So material science.
I think materials, yeah.
Yeah, I've heard a lot of the big American qubit scale-up plays are getting very worried, or worried is maybe the wrong word, very interested in the material science aspect of things. And reproducibility, like making very, very tiny things and having 10,000 of them being identical is like very hard.
Yeah.
It works really well.
Big flat services and all that.
Yeah, no, fair enough. Seems like an important part of the puzzle. Well, maybe talking about that puzzle and the future of quantum in Australia, it's a good time for our next question, which is, where do each of you see the role of researchers, academia versus industry in the quantum future here in Australia?
I guess the obvious role, or one of the obvious roles of academia is like the education, the training. So creating the workforce of people who are quantum literate and who are skilled in understanding things about how quantum computers work and how to build them. And that's a really important role. And I think Australia does really well at our education in quantum physics. And the students that I see coming through Monash are like, really, for some reason, really high achieving people do physics. I don't know why. But, so, yeah, it's just amazing that it's people. I'm always so impressed with the caliber of the students that come through. I think that's academia is probably one of the biggest things they can contribute.
I feel like when I compare like academia and industry, like academia is more into like foundations, like asking like the bigger questions, whereas like industry pushing more about like scalability, like making devices bigger and like use cases and stuff. And I think like if both of them work together, that's like pushing each other. So it's perfect.
Yeah, certainly agree. And I guess, again, I'm a product manager, so the thing that I like to see is getting products in the hands of people and being used and at scale. I think that's sort of what my job is all about, is actually getting products into market and being used. And so I think I see that as the role of industry, is to take a lot of the advances that are happening sometimes with academia and industry in partnership, but then turn them into a product that can be used and I guess generates some revenue. And revenue might sound great, money is always great, but actually I think having a commercial product that can be used to solve problems, I think that does a lot for improving, I guess, the appreciation for what quantum can do from industry. Like they can actually purchase this, they can do something useful with it. It grows sort of, I guess, confidence and awareness of what quantum's capable of as well, with something that they can actually, buy and put to work. So I think it's certainly a sort of a relationship between the two, but I think I see industry more on that side.
I mean, that's in itself is a pretty interesting conversation to even be having. Because if you think like 5-10 years ago, in the landscape of quantum technology work in general, it was almost entirely in academia. It was almost entirely in research labs. And you could get a grant to say, I'm going to put 2 qubits together. And that would be huge. And like you were competitive internationally doing that. And there's kind of this joke that like quantum computing is always like 5 years away, 10 years away, and it doesn't seem like it's ever actually getting anywhere. But the viability of that question about the role of industry now compared to 10 years ago, I think is like strong evidence that there is actually significant progress, because you can't really, as a researcher in a lab anymore, do a world-class qubit experiment unless you're doing something really unique. Like you can't just take the existing technologies and do a little bit more with them, because like IBM's got however many hundred of them now, and you can't do that on the scale of a research lab, which is like, whatever your opinions are about whether that's a good or bad thing, it is a sign of the fact that things have progressed and changed a lot.
I have multiple projects where I have industry partners, and I think that really helped my competitiveness in terms of getting funding. So seeing me as an academic paired with, a big corporation made my case much more appealing to the funders. And I think that's really helped me in my career get projects up, was being paired with industry.
Yeah. Yeah, and to your point about it's changed a lot. I mean, I certainly have not been in the industry for as long as my esteemed panelists, but nevertheless, I've been here for nearly 6 years with Q-CTRL. And certainly when I started, the sorts of cloud quantum computers that were available, sort of 2-4 qubits, like they weren't that large. And, I was trying to put together Black Opal as this, Duolingo for quantum, sort of quantum education platform. And a lot of it was just the promise. It was like, hey, in a couple of years' time, you'll be able to do something useful, we'll have robust, reliable qubits that you'll be able to do something with. That was 6 years ago. And then now, last year or two, you're looking at 100, 120 cloud-based qubits, a lot more robust, able to be put to use for non-toy problems. And so even in my much briefer career in quantum, that's changed a lot. It's changed a lot.
Exciting. All right. Well, let's move along. The next question I have for discussion is, how important do you think public outreach is going to be? So things like today, things like other public outreach efforts for the viability of the quantum sector in Australia?
I think it's really important because for a lot of people, quantum is still like some kind of, magic, which they know maybe from movies, just a word. And just explaining what we actually do with it or what it is, builds like trust in people that they actually invest in it. Like no matter if it's teachers explaining them, like making that a priority in their physics lectures, but also just people from other industries just thinking that this is interesting and trustworthy and not just some theoretical game.
Right.
Yeah. And outreach does a lot for that, I guess.
Yeah, you want people to trustworthy. You want to make sure that the hype is contained. And so I think these kind of things where you're trying to educate the public to understand better what the reality is important to treat trust and minimize hype.
Yeah, completely agree with both of you. I think in a lot of cases, people think that quantum is more nascent than it actually is. Like they don't realize that there are applications for quantum computing these days. They don't realize that if you wanted to, you could log on and use a quantum computer in the cloud right now. They don't realize that if you wanted to, you could learn to program a quantum computer fairly easily these days. So they think it's not for them. And magic and whatever else. And so I think a key role for this sort of outreach is changing that perception and making people realize that it's a lot more accessible than it used to be. And if it's something that you want to make a career in, then you can. It's just the barriers to entry have significantly lowered. And I think it's important to make people aware of that. So it's a choice for them.
Something to think about is as these technologies proliferate, does there come a time where we actually kind of stop talking about quantum as a word that we preface things with, because you don't because quantum physics really is just physics. It's just the way the universe behaves. And we kind of give it this special distinction because it's kind of currently topically a barrier we draw between devices we have and devices we will have in the future. And so does there come a point where these devices exist and are so reliable that we don't really have that barrier anymore and we don't necessarily need to keep talking about what quantum is? Like, how much does the layperson actually need to understand, I guess, is the question.
I hate using the word quantum. I actually like to call myself an applied physicist. Just as you said, quantum physics is physics, especially when you talk about something like magnetic resonance, which has been done for 70 years. And I work in magnetic resonance. It doesn't feel required to put the word quantum in front of it, but I still do because funding and
cut that from the recording.
I mean, I do quantum physics, but as I said, I don't think it deserves a special label, particularly.
I think in quantum computations, it's a bit different because, it's sometimes really important to make it clear that a quantum computer cannot do the same thing as a classical computer, and that these are really different. So in this category, I think I would like to keep the
You think that distinction remains like 20, 30, 40 years from now? Yeah.
It gets us on the panels as well, doesn't it? I don't know, but I guess I wonder as we see use cases develop over time. We mentioned things like these optimization problems or applying it to areas like scientific simulation, financial optimization, things like that. Maybe it starts to become just another approach for solving these sorts of problems that sure is distinct and applies in specific situations, but perhaps doesn't have to be this key completely different alien thing rather than another approach to solving certain types of problems. But maybe we're probably a little way away from that.
Yeah,
we probably should trade on the benefits of the name in the meantime. Maybe.
Definitely. Yeah, I guess I'm wondering more like it definitely seems like it makes sense at the moment to be like there's this thrust into this area of technology, but at a certain point, does that need to use that label kind of dissipate? I guess maybe in computing the answer is no. You'll always want to distinguish between the types of processes that you can accomplish with different kinds of tools, but maybe in other areas it becomes like less of a buzzword as it becomes more of an accepted thing. Okay, so with that said, next question. What do you want the public to understand about quantum physics, quantum technology, quantum science?
Basically what I just said. So quantum physics is just physics. It's exciting and it's difficult to understand and it's fun, but it is also something that we've been doing for a long time and we're really good at, and it isn't magic.
So I work in quantum machine learning, and I get a lot of emails like, oh, can you please run this on your quantum computer? And I want to understand, I don't have a quantum computer. I can run them, run experiments like whenever I want. So I feel like, for example, my dad just said some months ago, oh, my next laptop will be a quantum laptop. I don't think so. So I'm just understanding that, yeah, quantum is useful, but the quantum computing will be very different than also different use cases than the classical computers we use right now. So I don't think we will have a quantum smartphone because we can do everything with our smartphone today. Why would we like research in that direction, right? So I think I would like the public to understand that we are interested in quantum computing in very specific questions we can't or only barely can solve with classical computers, and we want to solve these kind of questions with the specific or new quantum computers. And yeah, it's not like an exchange for classical computers.
I think what I would like the public to understand is that quantum is for everyone, in the sense that, I'm here on this stage having, I'm not a quantum physicist. I didn't study it at university. And actually, I work for Q-CTRL. We have between 100 and 200 employees now. And probably half of those are not quantum physicists either. They are software engineers, designers, salespeople, marketing people, all working for these mature quantum companies that exist now. And once you get to a certain size and certain stage, you need this broader range of skill sets to work in a quantum company. But nevertheless, you need to be quantum conversant. You need to understand the fundamentals. You need to be able to understand the domain that you're in. But people often ask about, how they might get into quantum, into the quantum industry. And I guess what I would like to leave those sorts of people with is that there's never been a better time to get into the quantum industry, especially if you have these sort of quantum adjacent skills. They are also necessary in the industry now. Again, maybe a newer thing. But, you can learn the fundamentals and, get into the industry. So if that's something that interests you, then there's never been a better time.
Yeah, I guess it's a good point. Like, not everyone who works at Microsoft physically makes transistors. Like, there's a lot of other jobs associated with working at a very big company. So, fair enough. I just wanted to pick up on something that you said, Kerstin, the example of how the things that classical computers and quantum computers do are fundamentally different, and how the quantum computers that we hope to build will be useful for very specific kinds of problems, so it won't necessarily replace classical computers in most cases. I think that that's something that I think is, at least in like quantum literate people, I would say like fairly widely accepted, fairly widely understood. I do just wonder if we are going to look very foolish in 50 years, having said that, remembering there's that classic IBM example where someone's like, oh, there's in like the early days of conventional computing, some IBM executive being like, oh, there's probably a world market for like 7 computers. They're each going to be about half the size of this room we're currently standing in, but like most people aren't going to need one, and you're probably never going to use one unless you're working in one of these very specific areas. And now, I don't know, there's probably like nearly 100 computers in this room that have like more power than the 7 computers this guy thought was going to. So I don't know. I just wonder like if making statements like that is, or if there are like actually good reasons to think that there's a difference there.
I get your point, and I would be really excited if we all had quantum Apple Watches or whatever. But I think, for me at least, the classical computers are so good, and I don't think that we need anything more than this in our everyday life. But I don't know, I might be wrong. It would be that would be exciting.
Yeah, I'm sure they said the same thing about the telegraph at some point in the past, right? But yeah, no, I understand that there are like actual mathematical reasons to say that like this kind of computing is different, but just a thought.
Yeah, it may be something that maybe you don't all have a quantum computer in our pocket, but nevertheless, as with something like GPS, like quantum technology plays a key part in our lives more than we realize. For example, I mentioned some of these optimization problems earlier, the likes of optimizing traffic flows, things like that, where it could be that quantum technology has played a key role in making your bus run 15 minutes faster, but that doesn't mean that you have one in your pocket. Maybe it's those sorts of ways that it impacts our lives, perhaps.
Also the cloud access, just like, not everybody has to have one like, in their cellar basement, but just accessing them would be, I see that. Yeah,
we actually ran a workshop in the US just last week where people were programming a quantum computer from their phones using the IBM cloud computers running an optimization algorithm on it. So like, admittedly, it's not quantum in your pocket, but it's still quite a big departure from where we all, sorts of access we had to quantum computers 5 years ago.
We all rely on like atomic clocks, GPS now, and things like that. Quantum devices that are currently being used.
I guess also my point was more like, or also that some people think that, I have this problem and I solved it on my classical computers. For example, there was a group researching about some medical images, and they just wanted me to run their algorithm on my quantum computer, and then they thought that will be better or more accurate. And I think that's what I want the public to know, that you can't just translate things from classical computing into quantum computing.
And it won't necessarily be better.
Exactly. Yeah, it would be horrible.
Okay, good to know. Maybe following on from that question about the general public, what do you all wish that, I'm going to say policymakers, government, people who make important decisions about all of our lives knew about these technologies? And maybe to expand slightly, maybe Australia, maybe a lot of countries are typically very slow to legislate around a new technology. How do you think we are doing in the quantum space?
I can take that one, which not so much in the policy field, but I think at least in terms of what I would like to, sort of message I'd like to send would be that I think quantum is ready for sort of like this large-scale education piece where I mentioned at the start, we see this hunger within Australia, but also around the world in terms of wanting to learn quantum computing, especially as they get exposed to it. And we're seeing that at high school level, at vocational level, at enterprise learning and development sort of level. And I think as this generation, the next generation of students come through, I think quantum computing will be a tool in the tool set that people will, these students will need to be aware of. It might not be the thing that they do. They might not just do quantum, but in the same way that, an engineer, chooses a particular programming language for a particular problem or a particular database technology for a particular problem, quantum computing will be appropriate for certain types of problems as well. So understanding where it's applicable, when you would select that tool, I think for the students that are coming through now, that's going to become really important for them. And so I would love nothing more than, for every student that comes through from here on out to, graduate with a solid understanding of the quantum computing fundamentals. But that requires really, getting into these, curriculums at, state, federal level. Yeah.
It sounds like such a far cry and such a difficult thing, right? To think about like, this is like cutting edge science. How are we going to teach it at high school level? But the same has been thought before about a lot of, especially physics. Like I remember in particular, when you go to high school, this is like you typically in Australia, many other places, you do like a modern physics module. And the modern physics that you're learning is like 100-year-old physics. But the point is that it was cutting edge physics 100 years ago, only able to be understood by the smartest physicists on the planet. And you certainly weren't teaching it at a high school level. But now it's like year 10 physics curriculum. So maybe there is something about like a better pedagogy, better educational tools for like integrating this like complex stuff even earlier.
Yeah, I think we certainly underestimate what kids are capable of. We were showing off the very interactive that's here as part of this exhibition at a high school student sort of, not a jobs fair, but we're coming to see what they might want to study at university. And we had 50 people lined up wanting to play with the block sphere and learn quantum computing. So I think, and then they just got it. They just picked it up. They took to it like ducks to water. And so I think we often underestimate, to your point, about what kids are capable of, what they're going to be interested in, and sometimes it just takes getting it in front of them, and maybe the way that you teach it, I think, as well, making it really engaging, accessible, interactive. I think all of that stuff's really important.
One of the things we have problems with at university is attracting students to do experimental physics. So for some reason, a lot of students are more inclined to stay in theory. I guess maybe they think experiments are scary. So I don't know if this is a government policy thing, but it's something that,
make it mandatory. Experimental physics. I'm with you on that, Michael. That sounds good.
From age 5. But yeah, like trying to sort of encourage, working and encouraging like engineering and physics to mix. Because I mean, building a quantum computer is really just like engineering, essentially, like a lot of microwave and RF and optics and stuff just sort of shoved into a box. So trying to encourage the applied side of it is something that's very important to me in the education space.
Yeah, fantastic. Well, I think our next questions relate to they sort of connect back to an earlier point about the role of like academia versus industry, but more specifically in the context maybe of the Australian research environment, where Australia has made a history of funding these large 7-year projects, like Equus is one, the Australian Research Council Centre of Excellence for Engineered Quantum Systems. We've mentioned some of the other ones, Centre for Quantum Computing and Communication Technologies, even things like FLEET, the low energy electronics technology centres. We've got like a history of funding these long collaborative projects. And we've talked about how maybe like the shift from doing world-class maybe qubit stuff in the lab is moving to like more that's the purview of industry. What do we see as the role of large like ARC, Australian Research Council funded research centres in the future quantum landscape in Australia? Should we keep funding them? What do you guys think?
Yeah, I think they're really important to connect different groups like over the country, like different universities, connect industry with the right research groups, do outreach. I think, we have time and like focus for that, where maybe companies don't have so much like funding for, I don't know, teaching children, or I mean, this case is special, but generally. So,
not really their job so much.
Yeah, I think like the freedom you get in one of these research roles allows you to think of new ideas. So, I mean, I'm an example of this. So I got a job in FLEET, and while I was there, I thought of a bunch of ideas which ended up being, 5 years worth of projects and funding with industry partners. But if I hadn't had that role in FLEET where I was free to just think about stuff, then I probably wouldn't have had those ideas. So, I think it's important to have a place where people can just think about stuff and have the opportunity to do whatever they want with it.
Also, I think these centers just attract a lot of people outside Australia to come back or to just move here, because they provide a structure and you can just come and you will have a lot of people to collaborate with. And I think it's good. We should keep doing it.
Yeah. Or maybe a little bit of inside baseball for the researchers in the room, or anyone who has the ear of anyone who makes decisions about these things. But just about every researcher I know loves this ARC Centre scheme, thinks they're awesome, wants there to be more of them. And there's some rumor that they may be going away in the next revision of the ARC policies. So if you care about that and you talk to anyone who makes those kinds of decisions, tell them every academic loves the centres and to keep them alive. It's very important. Maybe a question for Kerstin specifically, having worked in Equus, which is one of the organizations that has helped put together this exhibition that you and I have both worked across. What do you think is going to be the legacy of Equus, which is coming to an end very soon in quantum space?
Yeah, I really think the best thing Equus did was connecting the people. That was so special to me. Like, it was so easy to visit other research groups and to learn so much. I'm a theoretical physicist my whole life, so I never visited a lab in Germany. But here it was so easy. Like, everybody invited me. I saw so much. I learned so much, and I progressed so much quicker just because of these connections. And they were left after the center ends. So I still know people in Perth and Brisbane. I know who I can talk to if I have this kind of problem or this kind of question. I know who is an expert in this, and this is so valuable. And another thing is, like, if you know a lot of people, you also know a lot of different people, which is really good if you search for role models, like especially as a woman in physics, you sometimes get a little bit lonely, and just having so many people to connect with and finding these special people you can reach out to is so important for your career.
Yeah. I think from my side, I guess it's been fantastic seeing some of the outreach work that Equus has done, organizations like Equus, especially, I guess, the variety of the outreach. So I know there's the road trip that's been done when going out to, Northern Territory, Tasmania, all sorts of parts of Australia, exposing students, communities, people that otherwise maybe would not have learned about quantum or even considered quantum as something that they might want to get involved with. I think that's extremely important. But I think also the diversity of ways that that outreach occurs. So, whether it's, a camp or a hackathon or art, I think having like lots of different ways that people are exposed to quantum, can learn about quantum, that brings more people in, makes it feel more accessible. And I think having a number of ways that people can feel that quantum can be for them and maybe choose to take that on as something that they're interested in, I think that's really important.
Yeah, I think we also feel that a lot of other research centers are looking at Equus and like saying, oh, you did this road trip thing. How can we be involved? How we can do our own things? So I think that will be just also a big legacy to inspire the next centers of excellence, no matter what they were researching about. But I think what Equus has done in outreach was really special and new. So yeah, I think that's a big part of Equus legacy.
Fleet style stuff from Equus, ID Factory and the translation seed funding as well. That was from Equus that Fleet used here.
Very good. Okay, well, any further comments from you guys on any of the stuff we've talked about? Anything else you just want to say about quantum? Any thing to add, or we can move to questions from anyone in the room who wants to know about anything we talked about or anything else relating to quantum. Seems like we have one down the front here. Do we have a mic running? We do.
Is it picking up? Do we need a mic? Thank you very much for your exposition. Is this question about the academia, educational institution, and industry now participating in the education and attracting and inspiring students, particularly for quantum science, technology, and computation, will be inevitable to a certain extent and sensing. But the participation of students, particularly from lower level, in STEM is very low in this country. And that is a worry for our country, very small in terms of population. Q-CTRL has a very good exhibition, but I may notice that only one qubit yet, maybe put on 2 qubits and see what happens. But in general, how can we fit the student into STEM area? Nevertheless, I understand that for quantum companies now, you don't need to be a quantum physicist. You have marketing people, you have software engineer and all sort of things, but fundamentally it's still coming from STEM, and we don't have that much participation in this country in particular, and actually the maths standard of our country is going backward in certain extent. So, I mean, industry and educational institutions have been working together and help that, but is there a way out that for this?
So
I have another question, but if I'm time,
would it be fair to say? Would it be fair to say the question is how do we get more people interested in STEM at an earlier age?
I can also look to fit into the system, working at research, well, lab in the past. Industry they funded a lot of research privately. Industry might be able to do that now, I don't know. But then the STEM participation in this country is a worry for the future.
Agreed. So, thoughts from the panel. How do we increase participation in STEM?
I think it starts in the schools. So you really have to make sure that the lessons, the school lessons are good and interesting. And that means you have to invest money into teachers and into, outreach events, into things where people or like students get fascinated of physics. And that's what you have to aim for. Otherwise, you can't force anybody. I mean, you can, but they won't become a happy...
You shouldn't.
They won't become a happy researcher. They are not fascinated. So I think that's where it all started. Yeah.
I come from a family of teachers, so I certainly support investing in teachers. But I do agree, you need to make it interesting. I don't know how we solve STEM in Australia, but certainly, when I joined Q-CTRL 6 years ago, my whole remit was, how do we make quantum computing education interesting to a broad population? And so we spent a year doing research, talking to people about why do they find quantum computing daunting, basically. So what's stopping you from getting into quantum? And at the time, it was, they might, it's hard to find reliable information in one place. You're just bouncing around, looking at textbooks, looking at all sorts of different things. It wasn't centralized. Oftentimes it was reading something that looked more like a university textbook and full of equations and things. And if this is the first time you've ever encountered quantum computing, that can be quite daunting. And also it was quite a niche pursuit, especially 6 years ago. And so you're often doing that alone as well, without necessarily a huge amount of support. And so one thing that we set out to with Black Opal was to solve those key problems, making something that's really visual, is written in a way that's a bit more entertaining and supportive, and is extremely interactive. And sure, this is a product that we sell, but I think also this gets used heavily in educational institutions. So, for example, in schools, in community colleges, where they want to be able to expose those students to quantum computing, but they don't have the expertise for that. And so that's where being able to give them some tools, some resources, that the whole point is to be really visual and really engaging. At the very least, hopefully that can remove some of those barriers, so that if they are interested in STEM, they might also become interested in quantum computing and not necessarily bounce off it. So it's a really hard problem to solve, but I think at the very least there's appetite from the educational industry, from the quantum industry, from academia to try to solve that better, I think.
Yeah, I'm not going to pretend that I can fix education in Australia. I don't know anything. But also that I wasn't a very good student, and I'm here. So I think I failed year 10 maths, and so I don't know my times tables, but yeah, I'm doing quantum physics. So
I think that's key, though, isn't it? Like, I think people perceive quantum computing, quantum technology as having such a high barrier to entry. And maybe it takes people like us to be on stage to say that it's a lot more accessible than you think. And whether that's the resources or just somebody in a position where they're teaching, to tell people that it's something that you can get involved with is really important.
Yeah, I think probably if you've chosen to come here on a Monday night, then you're probably not going to have not going to be a hard person to convince that this is a good idea. I think, for me, I agree with Kerstin. What everyone's saying, it starts in the schools. I also think it's a cultural thing, which is a little bit maybe deeper than just that. And I think that flows into the schools. So something, for example, one of the things that I'm fairly heavily involved with is this program called the National Quantum and Dark Matter Road Trip. And we drive around to schools all over the country, very remote schools, and we talk to the students and the teachers there. And the number of teachers in schools outside of one of the big cities in Australia who are teaching year 11, 12 physics, who have a physics degree, is almost zero. Very, very rare. And then that creates a flow of it. And these teachers are amazing people doing a very hard job, working very hard to do the best job they can. And they just they're afraid of the content that they're teaching because they don't, it was never taught to them very well. They don't understand it. And that flows onto the students. And it starts even like earlier. By the time you're in 11 or 12, you've selected to be doing physics. So that's fine. But like if in year 7, your combined science teacher doesn't like physics because they don't understand it, they're going to not do a good job of teaching physics, and then you're not going to understand physics, and you're not going to want to pick physics for year 11 or year 12. So it very much is a problem of the school system investing more heavily. Like I think like we've had researchers in Equus who've come over and we've tried to be like, oh, what are we going to do for like school engagement, school outreach? They've been like, oh, well, we'll develop this resource and we can send it to the teachers. And we've been like, oh, that's like way too complicated. The teachers won't understand it. And they've been like, oh, but don't the teachers all have physics degrees? Because in Canada, apparently, you have to have a physics degree to be a physics teacher at school, which is not the case here. And I'm not saying that necessarily should be the case because that's quite a barrier. But there is something there where we aren't teaching this stuff as well as we could be or should be. And then I think, yeah, it's baked into this cultural thing where like it's very hard to get people with higher STEM degrees to go and become teachers because we have this like cultural idea about what teaching is. And that's something that needs to change in order to get more STEM educated teachers to go into that space, I think, for my money. It's not, none of these are solutions. They're just things that I've observed and thought about, but I don't know how to actually do any of that.
I think there are also like new learning models that can work really well in those situations. So it is always going to be a tough supply and demand problem with, skilled teachers, especially that, skilled in maybe quantum computing or the latest aspects of quantum computing. But I can say, like, for example, we rolled out our Black Opal platform to 3,000 students in India last year. And they none of the teachers that helped to roll that out knew anything about quantum computing, but we're able to train them in the product, and then we're able to give that to students to use in a self-driven kind of way. And the teachers were able to help them use the product, and the product has sort of built-in support and things as well. So it means that those 3,000 students that otherwise would not have been exposed or been able to use to learn quantum computing at all were able to. So I think there's other modes, especially with students being so much more online these days. Everybody has a laptop in the classroom, those sorts of things. There's other ways we can deliver some of these materials to students without being hamstrung necessarily, I guess. So there's hope, I think.
Well, further questions?
Hello, this might be a really simple question for somebody who understands quantum physics. I am not that person. I wondered for Kerstin, you said before that a quantum computer will solve a really different problem to a regular computer. What kind of problems will a quantum computer solve?
It's a good question. That's a research topic. So, for example, I work in quantum machine learning, maybe it's a good example. So there are some patterns which are really easily detected by classical machine learning algorithms. We can, learn pictures or stuff like that. But we found that just because of the specific kind of quantum computer, like specific device structure, we can learn a specific kind of pattern much better on this device than on a classical computer. That's one example. Also, there are highly mathematical proofs that one algorithm works just faster than on a quantum device than on classical computers. So we can build algorithms specific for these new computers, which have nothing to do with the old computers. They work totally different, and then we can design them to solve problems. I don't know. Somebody can add to that.
Shor's algorithm, famous example.
Yeah, maybe you heard about Shor's algorithm.
Tell the people about Shor's algorithm, Kerstin.
No, I don't know.
Well, maybe higher level, some of the areas that we think quantum computing, maybe rather than specific algorithms, where we think it will be useful.
Yeah, so I think what helps me often to understand these kind of, because I have the same question. I'm doing research in this kind of area. So it's like, imagine you have a system of particles and they work with quantum physics. And then you describe them with a quantum device, which is itself like quantum. So it makes sense that you can describe the system and simulate it better with this quantum device than with a classical computer, which just has zeros and ones. So that's maybe a good picture to have in mind. So chemistry is a big application area. We're looking forward to do things with quantum computer and this thing to just simulate molecules and stuff like that.
Simulating biology and chemistry, famously very, very difficult with classical computers. Like, we still don't really know how proteins fold up. It's very, very complicated to compute, but maybe quantum computers could do it. I don't know, Mick, do you have any further thoughts on?
Yeah, so I mentioned these QAOA optimization problems.
What does that stand for?
Quantum Approximate Optimization Algorithm. And yeah, we're seeing a lot of use cases with that sort of class of algorithm. So for example, I mentioned earlier on sort of logistics, supply chain optimization, route planning, those sorts of problems that can essentially reduce to sort of a weighted network graph in some way. We're seeing a lot of utility for quantum computers, especially these hybrid classical quantum computers in those spaces. And you can imagine there's a lot of, I say things like supply chain, route planning, things like that, there's a lot of businesses, organizations in the world that benefit from those, incremental gains in those sorts of areas amounts to real commercial benefit, right? But those sorts of optimization problems generalize quite well to areas like portfolio optimization, stock picking, also to, what was the other one I was trying to think of? Like cybersecurity, fraud detection, things like that. So there's a lot of areas where businesses are already starting to make investments and explore real use cases in those areas on real quantum computers. And yeah, cybersecurity Shores was mentioned earlier. I mean, being able to implement Shores algorithms is a long way away, but nevertheless, even from a more practical perspective, you're seeing a lot of organizations, looking to implement, quantum-resistant encryption, things like that. So even just the promise/threat of what quantum computers will be able to do in the future is leading to businesses taking real steps in the industry today.
Fantastic. Well, I think that is close to us for time. So I think with that, I'll say thank you very much to our panelists here for that. And thank you all for coming. And I think we're going to be around for a while if there's any further questions or discussion. So yeah, thanks very much.